Hi everyone, welcome to the Princeton Reviews webinar, MCAT Spotlight Biology and Biochemistry. My name is Jenna and I will be co-hosting today's presentation along with our resident expert, Susie Greenman. Just so you know, everyone's lines are muted, so if you have a question or if there's something you'd like to share with us, please use the question box located in your go-to webinar bar. Also, we will do our best to get through everyone's questions, but if we are unable to answer yours, one of our experts will follow up with you afterwards. So without any further ado, I'm going to pass this over to Susie. Go ahead.
Hello, everyone. So my name is Susie, and today we are here to talk about the biology and biochemistry section of the MCAT. So welcome, and thank you for spending the next hour with me as we go through some of the higher yield points of the MCAT biochemistry sections. So today we're going to be going through just a basic overview of the MCAT. If you're here, you could be at various stages of your prep. Maybe you're just thinking about taking the MCAT and you have no idea what it means and what the MCAT comprises of. So we'll spend a few minutes talking about the basics and the breakdown of the MCAT. Then we'll go into a biochemistry review because the MCAT now is composed of 25% of biochemistry. So that means 25% of all of the sections will have biochemistry related questions on them. So whether that means it is a strictly biochemistry question or whether it means it'll be drawing from your biochemistry base. Biochemistry is all over the test, so super high yield. So that's what we're going to be focusing on. And then we'll do a sample passage if we have time and go over some of the resources that Princeton Review has for you available to help during your prep. So just a quick introduction. My name is Susie. I am currently a medical student at the University of Rochester in upstate New York. I've been with the Princeton Review teaching MCAT Bio since 2013 and teach all of the grad, not all of the grad. I teach GMAT, LSAT, MCAT, Psych, Soc, and Bio with the Princeton Review, and I am a premier tutor and teach online and in person. And for the last couple of years before going to med school, I was the graduate product territory manager in New York City, which means that I used to get to go around and just hang out with people who thought they wanted to go to med school and chat with you guys. So I love the MCAT. I am in love with med school, and I feel free to ask me any questions about the application process or MCAT or anything like that. I am here at your disposal. Okay, so let's get into the MCAT. So first of all, we are going to talk a little bit about what the MCAT is. So first of all, this is a really long test. You're going to learn as you go through med school that long tests are now the norm. So this is the first of a series of long tests. STEP, the USMLEs, all of those licensing exams are also very long, but this one, it's getting you right in there. So MCAT is 7.5 hours. It is given on a computer. Most of the time it's given in a Prometric test center, which are various testing centers throughout the United States, and they're all very standardized. You have, fingerprints and metal detectors whenever you go in, and almost every medical school in the United States and Caribbean and Canada requires it for entrance into both MD and DO programs. The total seated time is about 7.5 hours, but that does include breaks, which you can end early or skip entirely. So the 4 sections of the MCAT are broken down like this. So there's 59 questions for all of the science sections, and those are each 95 minutes. So the first section is the chemistry and physics section, also with a biochemistry portion. So chemical and physical foundations. The second section is CARS, and this is like the equivalent of a verbal section of the SATs, although I will say a little bit harder. There's only 53 questions in a 90-minute portion. Then you go into, you'll have a little bit of a lunch break, and then your biological and biochemical foundations of living systems. That's the biology, biochemistry, a little bit of orgo, and then your psychological, social, and biological foundations of behavior. So this is your psych, soc, and again, biochemistry. And then throughout all of the sections, you're going to be doing scientific inquiry and reasoning, research methods, statistics, basically looking at research and how it applies to all of these topics. So a lot of that is going to be a little bit challenging, especially if you're still in school and you haven't necessarily seen a lot of research. So the score ranges, you'll see here that each of the sections are broken up into from 118 to 132. Why? I wish I could answer that, but yeah, it's a mystery. So that means that your composite score is anywhere from 472 to 528. So your scores are based on the number of correct answers, meaning don't worry about getting any answers wrong. You want to get one answer for every question because you don't get any negative points for answering a question wrong, okay? It's not like the SAT. So that means that the mean score is 500, so 125 is the center score, right? That's the mean. And anything above that is above the mean. Each question is multiple choice, and there's only 4 answer choices per question, and there's both passage-based and freestanding questions. So, for example, in the biochem sections, you can have anywhere from 4 to 6 passages, anywhere from, I think it's 4 to 7 questions per passage. And again, no guessing penalty, never leave anything blank. A lot of people like to ask me what score they should aim for, and that really depends on what school you want to go to. You should know where you're aiming on going. And for information about what that school tends to accept, you can go onto the AMC website, and they have a great resource called the MSAR that has a list of typical entrance scores and GPAs and things like that. And you can tailor what schools you'd like to apply to and what your goals should be for your MCAT scores based on that. Okay, so that's the MCAT. Let's talk a little bit about the bio section, or the biochem anyway. So we're going to start with some thermodynamics. So the thermodynamics and kinetics are the basics. These are the underlying principles around everything that happens in chemistry, in biology. Why does anything happen? It all comes back down to thermodynamics. So when you think of thermodynamics, what do you think of? Gibbs free energy, of course, which is related to the first law of thermodynamics, that total energy is conserved. So delta G. Delta G is Gibbs free energy, right? Delta H stands for enthalpy. T is temperature in terms of Kelvin. And S is for entropy. Now, when we think about these terms, I could ask you what enthalpy means, and most of you would say heat. Okay. Yes, it is heat, but not exactly. I mean, isn't heat temperature? So enthalpy, it's more of a concept that isn't really described well. We can think about it in terms of heat. When heat energy goes in, our enthalpy increases, and when heat energy goes out, our enthalpy decreases, but it's not really heat, right? It's about the energy conserved within the bonds. In fact, we can liken it to something like potential energy. It is the potential energy that exists within the bonds that when those bonds break, that energy is released in the form of heat. So instead of thinking about it in terms of enthalpy, let's think about it in terms of potential energy. We can think about the energy stored in those bonds as being able to be released and be used for the reaction energy. And what about entropy? So entropy, 10 bucks says all of you are going to say randomness or chaos. But what does that mean? Or disorder. So it means we're talking about the organization of the molecules. So order meaning we have this lattice structure over here, the maximum order, right? A salt crystal or an ice crystal, versus chaos, where we are in the gas phase, where everything's just bouncing off each other and there's no order whatsoever. So we can think about it in terms of this, or we can think about it in terms of kinetic energy, the movement of the molecules, how we are already in movement and in the relationship of our movement with the environment that's already around us, which makes sense because it's also related to the temperature. And temperature is a measure of the vibration of a molecule as it exists in the environment now. So if we're talking about free energy, and the question of free energy is this reaction going to occur, right? That's what Gibbs free energy is actually asking. Is this reaction going to occur? If I put chemicals A and B into a beaker, am I going to get C without having to do anything extra? So if we liken this to physics, that means that if I put the ball at the top of a hill, is that ball going to roll down on its own? And in order for that to occur, my kinetic energy has to be greater than my potential energy. So my temperature and my entropy have to be greater than my enthalpy in order for my delta G, my Gibbs free energy, to be spontaneous, and my A plus B to create C without having to add any additional energy. So if my delta G is equal to 0, in our physics metaphor that we're talking about here, that means that my ball is stuck in the middle of the hill. It's going up and it's going down at the same rate. It means it's in equilibrium. So for Gibbs free energy, that means I've put A and B in a beaker and I'm making C, but at the same time, C is breaking down into A and B at the same rate. So my forward and backwards direct reactions are occurring at the same rate. When my delta G is greater than 0, that means that my delta H, my enthalpy, is greater than my entropy and temperature. So my potential energy is greater than my kinetic energy. So my ball isn't rolling down the hill. So it's non-spontaneous. A and B are not going to break up to create C unless I do something extra and add some energy. Maybe throw in a stir stick or add some heat or something like that, right? So this is a non-spontaneous reaction. So a spontaneous reaction has to have a negative delta G. And that means that if I throw A and B into the beaker, I'm going to get C without having to do anything. So spontaneous just means that the reaction will occur. It does not mean anything about speed. I can take millions of years to create compound C, or compound C can be created in a millisecond, okay? Spontaneous just means that it will occur. It has absolutely nothing to do with speed. Speed is determined by kinetics, which we'll talk about later. So the other thing about thermodynamics that we want to talk about is just the standard state that you'll get in free energy of a reaction. So we're not going to get into this very much, but on the MCAT, you will see this, and this is more related to what's happening right now in the beaker at this temperature when you have the gas constant value and given all of the parameters at that particular moment, and the concentration of the products and the reactants. So most of you will have already gone through this in your entry-level chemistry or entry-level biochemistry class, and if you were to come to a class with me, we would go over this more. But we're going to skip over this now. It would require nice practice questions and stuff like that. But let's talk about what would happen if you have a reaction that isn't spontaneous. So let's say that we have a reaction, like I said, A plus B making C, where my delta G is positive. So it's non-spontaneous. I put A and B into a beaker and I'm not getting C. What can I do? Well, I have another reaction in a second beaker, and this guy has a negative delta G, and it's negative 12, and he's creating a whole lot of heat. So D is breaking down into E and F. So what I can do is I can actually put these beakers together. This is called reaction coupling. If I put these beakers together, basically I combine, sorry, slide, there we go. If I combine the beakers, then my energy that's being released as D breaks down into E and F is enough to overcome the energy barrier that A and B need to create C. So that energy is all being put together, and now I have C being created. And the delta G's are going to be additive. So I'm going to have a delta G of -7. So the heat that's being released by D is absorbed by A and B. So for reaction coupling, we need to write the reactions together in order for it to count as coupling. And we use this in the body a lot because there are a lot of reactions that are occurring in our body that have a positive delta G. And if we want them to occur, we can just couple it with another reaction. What's a good example of a common reaction in the body that we use to couple things? Yeah, that's right, ATP. So ATP breaking down into ADP is a very common example, and the delta G is as high as -13, -12. So this is a very common reaction that we couple things with in the human body. Okay, so let's look at the reaction coordinate graph. The reaction coordinate graph is where we start talking about the relationship between kinetics and thermodynamics. So thermodynamics is all about delta G. So on this graph here, if we look here, this is as we move through a reaction. So this is the energy level of my beginning substrates, right? This is my reactants. And this is the energy level of my products. So the difference in the energy level between my reactants and my products, this is my delta G. So 3 here, this is telling me about my delta G. I'm going to put all these up there. So 3 is my delta G. It's the difference between the energy of my reactants and the energy of my products. If my delta G is negative, meaning that I'm rolling downhill, right? Then my energy of my products is going to be less than the energy of my reactants because it makes sense, right? I want to get to a lower energy state. If my delta G was positive, my energy of my reactants, the energy of my products might be somewhere up here. Okay, so this is my delta G, and it's not going to change unless I'm changing my reactants or my products. So 5 right here is the line that represents the energy of my reactants, whereas 4 is representative of the energy of my products. 3 we defined as delta G. 2 is the reaction energy. This is the energy that will be released at some point during the reaction. And 6 here is the energy level of what? This is the energy level of the transition state. So this hump that we go over, this is related to the transition state. In order for us to go through this reaction, I have to go through this intermediate state that doesn't actually exist within the reaction. I don't write it in there, but it is a transient thing that is temporary, but exists and is very high energy. And the energy required to get to this transition state is the activation energy. And this activation energy is normally pretty high. So the level of this activation energy is what determines kinetics. If I have a very high energy of activation, then my kinetics that means that my reaction is going to be slower than if I had a lower energy of activation. And I can change my energy of activation by stabilizing my transition state. And that essentially is kinetics. Kinetics is all about the energy of activation, number 1. And thermodynamics is all about number 3, delta G. And that's it. That's the simple answer. So the energy of activation, which includes number 6, the energy of transition, we want to be thinking about how can we lower the energy of activation. And what are some examples? What are some thoughts? Yeah, catalysts, enzymes, exactly. So catalysts. Catalysts are a protein or some sort of chemical product that has three major criteria. The first one is that it's very specific. That means that at least within the body, we'll come back to that in a second, but a specific catalyst is going to be specific for whatever it binds to, right? If we're talking about within the body, hexokinase is going to work with a glucose molecule, not going to work with a fructose molecule, only with glucose, okay? So it's very specific to what it works with. It also is going to change the activation energy. By stabilizing the transition state, we are lowering the energy of activation, and therefore we're speeding up the reaction. Also, it's regenerated after each cycle. So it's not part of the reaction. And because it's not part of the reaction, it's going to be regenerated. So we don't write it in the reaction. The energy of activation is going to be lowered because we've stabilized the transition state, and we're going to be speeding up the reaction. So question. What's the difference between an enzyme versus a catalyst? Yeah, so enzymes are a type of catalyst. They are a biological catalyst. Most of them are proteins, and they work essentially by having a particular 3D shape. Catalysts within a lab can be a little less specific. They can be a chemical product, and they can react with more than one thing. But within the body, an enzyme is a lot more specific. It is a protein, and it has to be a lot more specific because within a lab, we can control a lot of things, right? We can control temperature. We can control whether or not we move something, whether or not we put it under pressure. Within the body, we don't have the ability to control all of those things. But what we can do is we can control the specificity of our enzymes. All right, so an enzyme is a type of catalyst. Awesome. All right, so let's talk about enzymes. All right, so if we have an enzyme and our enzyme looks like this. So there's two different states of an enzyme. You'll notice here that there's a difference between this site. In one particular case, it's round, and in the other particular case, it's square. So my substrate is a round spherical object that would fit into the round site. That means that that site is called what? Yeah, that's the active site. Good. So each enzyme is only going to have one active site for a substrate. That means that only one site on an enzyme will bind to that substrate. It may be able to react to more than one substrate, which oftentimes a bacteria or a virus will take advantage of by binding somewhere to another type of active site. But most of the time, what we're talking about with that is what's called an allosteric site. That little wedge down here at the bottom, this is called an allosteric site. And an allosteric site is any other site on the enzyme that can bind to anything else, okay? So we have one active site for the substrate, and we have a whole bunch of allosteric sites. So the two different states that we see here of the enzymes are active, being relaxed or on, and inactive, tense or off. And you can tell because when I'm active, my substrate can get into the active site, versus when I'm inactive, my substrate wouldn't fit, right? This is the whole lock and key method. So how can I turn an enzyme on or off? Well, there are a couple different ways, right? Give me some examples. All right, so we have some dephosphorylation or phosphorylation. So phosphorylation can turn it on or off. We can go either way. Cleavage, so digestive enzymes need to be cleaved before they become active. binding of different things, allosteric binding. So some proteins need to be bound in an allosteric site, causing a conformational change that allows for the substrate to bind to the active site. So all of these allow for 3D changes that allow for the substrate to bind to the active site. There are other types of regulation. One of them is negative feedback. So negative feedback is when there's something downstream that inhibits an enzyme that's further upstream. So a product could inhibit either enzyme 1 or enzyme 2 or even both, okay? So as we build up the product, we're less likely to have enzyme 1, enzyme 2, or enzyme 3 working in this particular image. We also have what's called positive feedback. So positive feedback is when the product helps to create whatever was previously, sorry guys, we're having an issue with my slides. Positive feedback is instead of inhibiting, I'm going to promote something earlier on in the cycle. So a perfect example of this is the oxytocin uterine contraction cycle within childbirth. So around 34 to 36 weeks, the placenta around the baby starts to degrade. And as that happens, you start to get lower levels of progesterone, which normally when your progesterone levels start to fall, even when you're not pregnant, that's a signal to the brain, well, a signal to the body that it's time to start shedding your uterine lining, and that's menstruation. So it's time to start shedding your uterine lining. Your uterus starts to contract. As your uterus starts to contract, the baby's head starts pushing against the cervix. The cervix has stretch receptors in it. So as the baby's head starts pushing against the cervix, those stretch receptors get activated. And as those stretch receptors get activated, it's sending nerve impulses to the brain saying, hey, I'm getting stretched. And the brain recognizes this, sends a signal to the pituitary, hey, it's time to release some oxytocin. So the pituitary releases some oxytocin, which goes down to the uterus, causes the uterus to contract, which pushes the baby's head against the cervix, which causes the stretch receptors to be activated, which causes the oxytocin to be released, et cetera, et cetera. So this is going to happen more and more, and we're going to have stronger and stronger contractions until we get to about 40 weeks when the contractions are so great that we push the baby out. So for positive feedback to occur, we must have what's called an external regulator. There needs to be something that will allow this to stop. So this could be, in this particular case, the external regulator is the removal of the baby. It's removing the relationship between the contraction of the uterus and the signal heading to the brain, right? Because when you contract the uterus, it's the baby that causes the stretch receptors to be activated. So removing the baby and you stop the positive feedback cycle. So that's really the only positive feedback system that you'll have to know for the MCAT, but it does come up sometimes. All right, so that's regulation. So let's talk about rates of reaction. So rates of reaction, we're talking about at what rate are we creating the product of whatever it is that we're making. So our y-axis is the rate at which we're creating our product, and our x-axis is the amount of substrate that we have. So we're starting out with no substrate at all. Let's say that we have a beaker with a certain amount of enzyme, and we're adding dropperful by dropperful a little bit of substrate. So as we do this, at first we're going to have almost no substrate, right? Our enzyme concentration is going to greatly outweigh our substrate concentration. And as that occurs, as I keep putting in a little bit of substrate, every time my substrate's going to find an enzyme active site very, very quickly, and my substrate's going to react right away, and I'm going to get my reactant. So as quickly as I can add substrate, I'm going to get my reactant. So I'm going to have this, what's called a linear curve at the beginning. As quickly as I can add it, I'm going to get my reactant. But as I keep going and I keep adding substrate, eventually I'm going to get to a point where my substrate concentration is about equal to my enzyme concentration. And here I'm adding a substrate molecule, and maybe my substrate molecule needs to travel a little bit before it finds an active site that is unoccupied. So it's slowing down a little bit. It's not exactly saturated, but it's nonlinear. I'm starting to slow down. So after that, if I keep adding substrate, eventually my substrate concentration is going to increase past my enzyme concentration. So at that point, my enzyme is completely saturated. All of my active sites are constantly being used. And even if I keep adding more substrate, nothing can happen because it's the enzyme active sites that are determining at the rate at which I can produce my products. So at that point, I'm going to get this saturated linear line, okay? And that point, that saturated point, is what's called my Vmax. So my Vmax is a constant, and this is for a particular enzyme concentration, not for the substrate. It's not dependent on the amount of substrate. It is entirely dependent on the amount of enzyme, the amount of active sites available for this reaction. So that's one way to look at a reaction, one way to define the characteristics of a reaction. Some other things to look at for characteristics of a reaction are what? You guys give me some examples. Yeah, Km. So Km is defined as the substrate concentration at 1/2 Vmax. So if I am here at Vmax, I go down to 1/2. I follow it until I get to my line and go down to my x-axis. This is my Km. This is the substrate concentration at which I am at 1/2 Vmax. And this is giving me information as to how quickly am I getting to Vmax. So my Km is related to my affinity. My Km is inversely related to my affinity because if I'm able to reach my Vmax quicker, meaning my affinity is higher, my enzyme is reacting with my substrate faster, and the quicker that I can react with my substrate, the quicker that I can hit my Vmax, right? So my Km is going to go down because this line is going to get steeper. So my Km is inversely related to my affinity. So I can mess with my rate of reaction by introducing inhibitors. So there are 4 types of inhibitors that you need to know for the MCAT. First one is competitive inhibitor. After that, you've got your non-competitive, uncompetitive, and mixed inhibitors. So the things that you want to know for each of these inhibitors are the binding site, how it affects Vmax, how it affects Km, and then what is it going to look like on when you go back to that particular map. So where does a competitive inhibitor bind? It binds to the active site, exactly. So it's going to bind to the same site as the substrate. So if 2 things are competing for the same site, for the question of Vmax, you want to ask yourself, if I am given an unlimited amount of substrate, am I going to be able to outcompete whatever it is that is competing for my active site? And the answer is yes, right? Eventually, I'm going to be able to outcompete it. I'm going to be able to saturate and put enough substrate in there that I have 1,000,000 to 1. So my Vmax for a competitive inhibitor is going to be unchanged. What about my Km? For Km, you want to ask yourself, am I changing my affinity? And I am, right? My affinity is going down because my affinity is being changed by the fact that the inhibitor is affecting the ability of my substrate to bind with my active site. Sometimes my substrate will get into my binding site and a inhibitor, the competitive inhibitor, might push that substrate out. So that means that my affinity is going down. And if my affinity goes down, my Km goes up. Awesome. Okay. So my Km goes up, my Vmax is unchanged, and I know that my binding site is active. So what does this look like on a graph? So this is what we had before, right? So my Vmax is going to stay the same. My Km is going to increase. So my new line is going to look something like this. And for the MCAT, you need to be able to recognize an inhibitor and what it looks like on this kind of graph, and also a Lineweaver-Burke, which we'll talk about in a minute, okay? So Lineweaver-Burke, and this kind of graph is called a Michaelis-Menten, okay? All right, so our next type of inhibitor, a non-competitive inhibitor. So what's the binding site for a non-competitive inhibitor? Yeah, it's the allosteric site, exactly. So what happens for the Vmax for a non-competitive inhibitor? Is it going to be changed? Yes, it's going to be changed. So what happens? A non-competitive inhibitor binds to an allosteric site. And if it binds to an allosteric site, it's going to change the conformation of the protein. Basically, it's going to turn it off. And it's not going to turn it off permanently. Remember, when we were taught, you always want to assume reversibility. It can always fall off. But let's go back to this slide here. If I have something that binds to an allosteric site, I can turn it off. That was part of the whole regulation thing, right? So I have something that binds to an allosteric site here and turns it off. So now my active site no longer fits my substrate. So this inhibitor, this non-competitive inhibitor, basically turns off my enzyme. So allosteric site, so if I turn off my enzyme, I'm decreasing the amount of active sites available and therefore decreasing my Vmax. But what's happening to my Km? So for Km, you want to ask yourself, okay, what's happening to my affinity? But you're asking yourself, what's happening to my affinity for my active enzyme? Only the active enzyme. For my enzymes that are remaining active, my affinity has not changed at all, right? I've taken active sites out of the running. I've turned some of the enzymes off, but the ones that are on, nothing has changed. So those guys, completely unchanged. So what does that look like on a graph? All right, so these were our two previous guys. So I know that my Vmax is going to go down, but my Km is going to remain unchanged from my first line. So it's going to look something like this. And this is very much an estimated graph, but I'll show you a better version in a couple minutes. So our third one, uncompetitive. All right, so where does an uncompetitive inhibitor bind? So this guy's a little bit different. He binds at what's called the enzyme substrate complex, which means that he binds to the enzyme after it's already bound to the substrate. I like to think about this guy as like a staple. So the enzyme binds to the substrate, and then the uncompetitive inhibitor comes in and binds to the enzyme and basically staples them together. If he binds over the substrate active site, right, then he's just not allowing the substrate to leave. So if he's not allowing the substrate to leave, then he's keeping them together, but he's also at the same time taking that active site out. Because remember, an enzyme is supposed to bind to a substrate, do its thing, allow that substrate to become the product, and then let that substrate go, and then react with another substrate. So if I'm stapling it to one substrate, then I'm essentially taking that enzyme out of reaction. So for my Vmax, what's going to happen? Yeah, my Vmax is going to go down. I've taken enzyme active sites out of reaction because they're stuck to that substrate. But if they're stuck to that substrate, what's happening to my affinity? Well, my affinity is completely going up, right? Affinity is like a measure of how stuck together are they. So the stickiness, let's say. So if my affinity goes up, my Km goes down. All right, so let's look at this one on a graph. So those are my last 3 lines. So my Vmax goes down, my Km goes down. So my new line is going to look something like this. Yeah. All right. So let's look at the last one, mixed inhibition. So mixed inhibition, as the name implies, is not exactly as straightforward as the other ones. And if you get a question about mixed inhibition on the MCAT, you're going to be given more information, okay? This isn't going to be like, you have a mixed inhibitor, what happens to Vmax or what happens to Km? You're going to be given a little bit more information about how it works in order to be able to answer the questions, because there are a lot of ifs, ands, or buts. The binding site for a mixed inhibitor, it prefers the enzyme substrate complex, but it can bind just a standard allosteric site. The only thing that you know for sure about a mixed inhibitor is that it lowers Vmax, which is what makes it different from a competitive inhibitor, okay? It must change the Vmax. But the Km can go up or down. So it can act similar to an uncompetitive inhibitor as like a staple, or maybe it binds to an allosteric site and kind of opens up the active site so that it fits it less well. Maybe it like opens up, making it more oval shaped, so the substrate's more likely to fall out, right? So mixed inhibitors, you're going to be given more information in order to answer any questions about that. It'll be in the form of a passage or something like that. Okay, so if you're given information or if you're given a question on inhibitors, a lot of times it's going to be in the form of a graph. So you'll be given a graph like, oh, reaction 1 looked like this, and then we put in compound 1 and it looked like this, and then we put in compound 2 and it looked like this. So compound 1 is what kind of inhibitor? Well, you want to ask yourself, what happens to Vmax and what happens to Km? Well, Vmax doesn't change, and there's only one kind of inhibitor where Vmax doesn't change, and that's a competitive inhibitor. And my second one, my Vmax does change, and if I were to calculate my Km, I would see that my Km changed to the point where I'm a non-competitive inhibitor. Sorry, did not change. So that's the Michaelis-Menten. The second one that you need to know is the Lineweaver-Burke plot. So the Lineweaver-Burke is essentially the same information, it's just the inverse plot. You just do everything and put it 1 over. So the x-intercept here is -1 over Km. The y-intercept is 1 over Vmax. And then the slope is Km over Vmax. So the information is exactly the same, it's just plotted in a straight line instead of your nice little curve. So if we look at what that means, so for a competitive inhibitor, remember you hit the Vmax, but your Km is going to decrease. So your y-intercept would stay the same, but your x-intercept would get closer to the origin, right? Your non-competitive inhibitor, your Km stays the same, but your Vmax goes down. So your Vmax would get further away from the origin, but your x-axis, your x-intercept would stay the same. And if you had an uncompetitive inhibitor, they're going to be parallel because the ratio at which you're changing things is going to stay the same. But both your Vmax and your Km are going to go down, so the line is going to move away from the origin in both the x and y directions. Okay, so these are graphs that you're going to need to recognize. You're going to be able to you're going to have to look at these graphs and be able to recognize what kind of inhibitor you're looking at. It's a pretty common question type. All right, so the information that we just went over is a lot of information. Honestly, we would have gone over most of this stuff in about at least a class, probably a class and a half. And so I know that this was a little overwhelming, and a lot of stuff we just brushed over. So I don't expect you to have learned all of this in the 45 minutes that we've been talking. But at least it gives you an idea of the depth that you would need to know these concepts, and also an idea of how we would teach these concepts. So I want to go into a sample passage and just kind of look at what that would look like. For those of you who haven't seen an MCAT passage before, what does that look like? But before we do that, let's just look at some basic strategy questions, some basic strategy at all. So when you're looking at answer choices, using process elimination is honestly your best tool. I'd say like probably 80% of the time you're able to get to the right answer simply by eliminating wrong answers. And a lot of the ways that you're able to eliminate wrong answers is by finding patterns in wrong answers. So wrong answers can either be too obvious, like, oh, that's definitely something that they would like me to choose, like it feels like a trap, or a partial answer. Maybe, yes, that's correct, but it doesn't answer the question. Or maybe it is giving an answer, but it's not giving the correct answer, or something like that. Extreme wording, always, never, things like that. Those, anytime that you see always and never in an answer choice, you almost always want to cross it out. And units, especially for biochemistry and physics questions, units are a dead giveaway. You can get rid of so many answer choices just by looking at the units. So, all right. This is what a passage may look like on the MCAT. This is a little bit of a short one. So we have on the left your passage, and you would always want to scroll up or down, see if there's any figures. Here we're not given figures, we're given different reactions. And I purposely chose a shorter passage so we wouldn't have to scroll up or down. And you'll see that this is about cancer, that we're talking about glycolysis and oxygen consumption, oxidation, things like that. And then if we go down to the reaction, we'll see, okay, this is a lot of glycolysis information, different carbon skeletons as we move from glucose to pyruvate. Yeah, this looks a lot like glycolysis. And then reaction 2, pyruvate to lactate. That looks like fermentation. Okay, so if we go to the question now, you don't need to spend a whole lot of time on the passage, right? You can go straight to the questions and answer them. I'm going to actually show you a sample passage in a second, but I just wanted you to see what this looks like. On the left, you have your passage. On the right, you have your question. There's only going to be one question per page. You're going to have to skip back and forth. So you want to use your scratch paper to keep yourself organized. And then you're going to have a periodic table. You're going to have the ability to mark questions and go back and forth. And that allows you to take the test at your own pace and also at the order at which works for you. Knowing what question types are easy for you is really important because those are the ones you're going to do good at. So look for those and take the test in the order that makes sense to you. All right, so again, a nice short passage. Take a second to read this. All right, so this is a pretty straightforward question. So we're talking about fermentation. So we know that fermentation is an anaerobic process. The final acceptor of electrons from NADH, well, we can use process elimination right away, right? We can get rid of oxygen because we know that that this is an anaerobic reaction. And the final acceptor of electrons, it's definitely not going to be NADH because we just created NADH from NAD+. So it's not the acceptor of electrons. So, okay, we're down to an alcohol versus an organic compound. So let's think about it. What is the acceptor of an electron for NADH? If we go back here, let's take a look. So we're making either lactic acid or ethanol. But what's the acceptor, right? So there's no alcohol here in this particular reaction from pyruvic acid to lactic acid. There is no alcohol. So we can automatically eliminate this because it's asked specifically in all fermentation processes. And when we're talking about an electron receptor, we want to be looking at what it is that it is accepting it. So the pyruvic acid is what's accepting it here, right? The acetaldehyde is what's accepting it here. So an organic compound. Let's do one more quick one. So during alcoholic fermentation, the molecules pyruvic acid and acetaldehyde are respectively. All right, so this would require you to understand the simple terms decarboxylated and reduced. So let's start with reduced. So if we're talking about oxidation and reduction, we can go to our trusty friends, oil rig. Oil, meaning oxidation is loss, and sorry, oxidation is loss and reduction is gain. So we have the molecules pyruvic acid and acetaldehyde. Are they going to be reduced or oxidized? So this is what's called a 2x2 question. So we're being asked about reduction or oxidation, whether it's decarboxylated and phosphorylated. So if we can figure out whether it's oxidized and or reduced, we can eliminate a lot of the answer choices. So let's start there. So pyruvic acid, is it going to be oxidized or reduced? So are we going to be gaining or losing electrons? So as we move from pyruvic acid to lactic acid, we notice that we're gaining what? Well, we're gaining some hydrogens, right? And hydrogens are a sign that we are gaining electrons. So we're being reduced. Same thing for when we move from acetaldehyde to ethanol. So we know that we're being reduced. So we can get rid of D. Oh, I see, respectively. Okay, sorry about that. Okay, so is pyruvic acid being decarboxylated or reduced? And then acetaldehyde, what's happening there? All right, so sorry, we were looking from pyruvic acid to lactic acid. So from pyruvic acid to acetaldehyde, I'm losing a CO2. So decarboxylation means that I'm removing a carbon. So that sounds like decarboxylation to me. And then from acetaldehyde to ethanol, I'm gaining hydrogen. So oil rig, reduction is a gain of electrons, and a gain of electrons can also be shown by gain of hydrogen. So decarboxylated and reduced. Okay, so that's how we would go through. We would continue and go through the questions together. But as we run out of time, I just want to talk a little bit about some of the materials and resources that are available here at the Princeton Review for you, okay? Getting into med school it's almost a traumatic experience. It is hard, from taking the MCAT and taking the prerequisites, not just for the MCAT, but for your application, all the way through to interviews and figuring out where you want to go once you get more than one acceptance. It is a tough thing. So we are here to help you, okay? When you're still in school, or if you are doing a post-bac program, we have a couple of things that are available for you to help you get through those requisites. these pre-med resources. So we do have some tutoring programs that are available, and they are basically on demand by minute. So if you're, stuck on a chemistry concept, you can just jump online and ask a question to your tutor and get through that one particular question. These guys do biology, anatomy and physiology, organic chemistry, whatever. They are always available, and you can just jump on 1 minute, get your question done at 4 o'clock in the morning, right before your big test, whatever. This can be something that will help you keep your GPA up, which honestly will help your application immensely. And then, so that's the pre-med GPA booster, but then there's also things like we have a free practice test available as you're getting ready and you want to see where you stand and how much prep you need to do. And then analysis, we have people on hand to help you analyze what that test means, as well as you get a nice little printout when you're done with your free practice test that helps you recognize your strengths and your weaknesses and where you should be focusing. And then we also, of course, have MCAT prep. So that means classes, self-paced material online, books, all sorts of things. It's like Christmas for MCAT. And then we also have a new entirely separate division for MCAT admission counseling. We have different webinars online that you can go and watch on your own time, things like how to ace an interview, or what your CV should look like, or what to write about for your personal statement, things like that. And we also have more personalized one-on-one services available. So that's something you can look into if that's something you're interested in. But basically, regardless of what your budget is, what your timeline is, there is something available for you, whatever you need, okay? The admission counseling is super helpful, especially if you are, for example, a non-traditional student, someone who's been out of school for a while and you don't know exactly how to market yourself, or if you don't have access to your pre-med advisor from your undergraduate university. Or if you don't have the greatest GPA, but you're really set on going to med school, this is exactly what admission counseling is good for. So those are things that we have available for you. I really enjoyed working with you guys today, and I hope that this was helpful in terms of giving you an idea of what the MCAT looks like, in terms of what a class with the Princeton Review could look like, and just kind of giving you an intro as you start down this path of med school and MCAT prep. If you have any questions, you can feel free to send an email to questions@review.com. Also, me and Jenna will stick around after this to answer any questions. Also, Jenna has kindly provided a nice little promo code. So if you are interested in signing up for a class, Fall MCAT 300, the promo code is good until October 17th, okay? It's $300 off all of the classes, in person or online. And I will be around to answer any questions. So I appreciate you spending your time with me, and I hope that you enjoy the rest of this lovely day. And thank you very much.
Hey, Susie, one thing I just wanted to add is that if you'd like to check out any upcoming webinars, you can head over to princetonreview.com/webinars. This is our MCAT week, so we have a couple things coming up. But again, thank you so much, Susie, for helping us tonight, and we really appreciate it.
No problem. Thanks for having me.
Absolutely. Have a good night.
You too. Thanks.